Hello and welcome to the unit of study Structural Mechanics. Now the objectives of this video is the explanation of loads and transfer of forces, and secondly we're going to be explaining types of supports in a structure. So to begin with, initially, what is the point of a structure? Obviously it's to transfer loads down to the foundation effectively without any failure. So how do we transfer loads down? Step by step. We start off by having the floor area. Suppose this is our floor, okay? When we have a floor, it's usually a force per area, right? So it's usually a force per area because if this is the area of the floor, we can place different objects around the floor at different positions. So the way we calculate the force on the floor is actually a force per area. And the units for this force per area is kilonewton per meter squared, which is kilopascals, Newton per meter squared, which is pascals, or Newton per millimeter squared, which is megapascals. Now it's extremely important to understand how to convert these and to remember your units efficiently and properly, because if you make your units inconsistently, you can result in massive errors in your calculations. So make sure you know how to convert units properly, and the most common used one for a force per area is kilonewton per meter squared. Okay, so sitting below the floor area we have the secondary beam or a joist, okay, and let's say we have this beam right here. So the beam is, you see the two supports, the triangle and the circle, and that's the beam. Now the floor area exerts a uniformly distributed load, which is this one over here, on the beam. So that this floor area sits on top of the secondary joist and it exerts a uniformly distributed load, which looks like this, and the uniformly distributed load is a force along its length. So it's actually kilonewtons per meter, whereas here it's a force per area, kilonewton per meter squared. This force per area is exerted on the joist and it's per the length of the joist, so it becomes kilonewton per meter, and this is the uniformly distributed load of the secondary beam. Okay, so what sits below a secondary beam? We have something called as the primary beam. So once again, I have a primary beam here at the bottom. Once again, my beam has the supports, this triangle and the circle. I'll explain what these are in the following videos, but the point of this is just to understand how we transfer loads down. So below the secondary beam we have a primary beam. Okay, the way this works is the following UDL, okay, the following secondary beam, excuse me, sits on top of the primary beam and exerts point loads on the primary beam. Okay, the way this is drawn is you can imagine the primary beam sitting below the secondary beam at right angles to it. So the secondary beam is actually causing point loads, so one load here, one load here, one load here, individually on the primary beam, and the units for a primary beam, the force, is calculated as a kilonewton. Okay, and then below the primary beam we have a column. Okay, and the primary beam essentially exerts one massive point load on the column, and this is also measured in kilonewtons. So just a quick summary of this. We have the floor area, which is a force per area because we have different objects lying around, so we measure this as a kilonewton per meter squared, which is kilopascal most commonly, but it's important to remember your units. Okay, and below this we have the secondary beam. The floor area causes a uniformly distributed load about the secondary beam. And thirdly, we have a primary beam. The secondary beam causes point loads about the primary beam, and the primary beam finally causes one massive point load on the column, which is in kilonewtons as well. Okay, so what do we have next? Next we review methods of resisting or transferring forces. So one of the most common forces you see is tension. For example, look at the following steel coupon. Okay, so we have this initial steel coupon. It's subjected to a tension force, so we have one tension force here and one tension force here. Imagine this tension force is equal in magnitude on each side. The only thing is it's opposite in the direction because it's pulling it from each side in the opposite direction. So that's what tension is. A tension is a force that is measured in kilonewtons. Okay, and eventually, if a member fails by tension, excuse me, we have something known as necking. Okay, and this is necking over here. You see, it's going to fail at its most critical location. For example, in this one, the most critical location is the middle, and as you can see, it's strained and it became thinner. Okay, so that's what necking is called. And bear in mind that this picture is fairly exaggerated, okay? But I'm just trying to show you what happens if we fail by tension. So we have something called as necking, and that's the phenomenon caused by the tension and failure, okay? So where can we see tension? Examples, we can see tension in trusses. And in a truss you have different elements, so different elements can undergo different things. Like in a truss, for example, you can have compression, tension, or neutral. Some members don't do anything, but they're there for the sake of making a truss stable and statically, just for making it stable, most commonly. Okay, and we can also find tension in cables in a bridge. For example, if you look at this bridge here, we have tension in the cables. Okay, so that's one of the most common forces known as tension. The second most common one we see is compression, which is also measured in kilonewtons. So compression is just the opposite of tension. For example, if you look at each side of this following element, we're pushing inwards towards the center over here. So these two forces, imagine, are equal in magnitude, and they're pushing both into the center of the compression, center of the structural element, excuse me. Eventually, by failure, we have something known as buckling, which is the following phenomenon here. Okay, so it buckles out of plane. The following shape is actually out of plane, so looking into the page, and that's the phenomenon known by failure and compression. Next, we have an extremely important phenomenon known as bending. Okay, so bending, what is bending? Obviously it's just bending of an element. Okay, you can have bending about the strong axis, the x-axis, right? So as you can see here, x is the horizontal axis, it's bending about the horizontal, which is the x-axis. This is known usually as this usually to determine which one's the stronger axis, excuse me, there's something known as the second moment of area, and it depicts which one is the stronger axis, and this will be explained in the future. But usually the higher the second moment of area, so usually the x-axis has a higher second moment of area, Ix, so it makes it the stiffer axis and the stronger axis. So what is the stronger axis in bending? It actually means it's much harder to bend about. It's stiffer, it's harder to bend about the following axis. Next we have the y-axis over here. It's bending about the y-axis, since the y-axis is the horizontal, as you can see here, and in this case it's the less stiffer axis, so it's the weaker axis. Next we have, and bear in mind that bending is like, it's measured as a moment, and the forces are kilonewton meters. Okay, so far we have tension in kilonewtons, compression in kilonewtons, bending in kilonewton meters. Next we have shearing. Now what is shearing? Shearing is a force caused by the rubbing of two elements. It's also measured in kilonewtons. For example, we have this bolt connecting the following structural elements, this one here and this one here. So these two rub against each other and can cause failure among the following cross section of the bolt. This is known as the shear plane, and usually that's where the bolt fails first, in the plane where it connects the following two elements. This is known as shearing. So shearing is just the rubbing of two structural elements against each other. Okay, think of it like, but try rubbing both your hands. That's what shear forces are. Okay, so we've reviewed tension, compression, bending, and shear. These are the most common forces we're going to be seeing in the following unit of study. Okay, and finally in this video I'm gonna quickly talk about types of supports. So the first type of support we have is a pin support. So like I drew the beam earlier in the video over here. So this beam over here, we have a triangle and a circle. Okay, so these are just the type of supports, how we represent them in this unit of study. So first we have a pin, which is a triangle. So a pin has two reaction forces, vertically and horizontally. What does this mean? It's vertically restrained and horizontally restrained. So it can't move up and down, and it can't move left or right. However, it can rotate because there's no moment restraint. Okay, so a pin has a vertical and horizontal reaction force, which means it's vertically and horizontally restrained. Next we have a roller. Okay, now a roller is exactly like a pin, except it only has a vertical restraint, a vertical reaction force. So it cannot move up and down, but it's free to move left or right. As you can see, there's no horizontal reaction force, and there's also no moment force, so it's free to rotate as well. Okay, so far we've seen pin and roller, which are fairly similar, and finally we have a fixed support, which is represented like this. As you can see, in a fixed support we have a vertical restraint, a horizontal restraint, and a moment restraint. This means it cannot move up or down, it cannot move left or right as it's horizontally restrained, and finally it can't rotate because there's a moment restraint as well. Okay, so types of support one more time. We've got a pin which is horizontally and vertically restrained, so it can't move up and down or left or right. A roller which is vertically restrained, so it can't move up and down. And finally a fixed support which is restrained vertically, horizontally and rotationally. So that's all for the first video. Thank you for your patience and listening.